Hello, my name is Pietro Sacchi and I am a PhD student at the University of Manchester, and today I will be presenting a work with the title Same or Different? That is the question. Identification of crystal forms from crystal structure data. This work was published recently on Crystal.com together with my supervisor Aurora Cruz-Cabeza and in collaboration with Matteo Lusi, Elisa Nawa and Professor Joel Bernstein. Sadly, Professor Joel Bernstein passed away in January 2019, however he still had many ideas in this work. Before I proceed, I would like to acknowledge the University of Manchester and my sponsor Lily and the Crystal Chemistry and Particle Process Engineering Group at Manchester. And I would like to thank the GCI, the Giovani Cristallografi Italiani, for organizing this wonderful event. Researchers working on the solid state deeply rely on the comparison between crystal structures to be able to identify crystal forms. They might be studying polymorphism or phase purity, or they might be interested in isostructurality. The method of choice for the characterization of crystalline materials is, of course, the collection of diffraction data, be it from single crystals or from powders. And experimental data is then normally compared with data that is stored in databases, such as the Cambridge Structural Database, the CSD, which has over 1 million deposited crystal structures, both organic and metal-organic. The simplest way to compare two crystal structures is to compare their unit cells, and this is the direct numerical comparison between lattice parameters, each with their associated errors. However, if the data is collected at different temperature and or pressure, the comparison might be difficult. Another way is to compare the powder diffraction patterns. This can be done visually or numerically, and impurities can be identified. However, once again, the patterns might be very different if data has been collected at different temperature and pressure. And also sample preparation issues can be present, such as preferred orientation, for example. If structural data is available, we can compare the crystal structures directly. And this has the advantage of ignoring the cell metrics. And it can be done automatically through algorithms like, for instance, COMPAC or XPAC. However, especially for COMPAC, only ordered structures can be processed. Another way to compare the structures might be to compare the Hirschfeld surfaces and the fingerprint plots. Once again, the cell metrics are ignored, and intermolecular contacts. So the intermolecular environment is highlighted. However, once again, we need structural data to be available. Amongst these methods, two of these, the powder pattern comparison and the crystal structure similarity comparison, are implemented in the CSD Python API, which is the programming interface of the CSD, and thus can be calculated for many structures. The powder pattern similarity tool compares powder patterns that are simulated from CSD structures, normally using default parameters, and in our case using only atomic positions, thus ignoring thermal displacements. It uses a normalized cross-correlation function, which returns the value from 0 to 1, 1 being the identity between patterns and 0 being a diversity limit. According to literature, we chose to use 0.965 as a threshold value for similarity. The crystal structure similarity tool instead compares clusters of molecules, 20 in our case, by overlaying them and finding the number of matching molecules for these clusters, together with the root mean square deviation for this match. If 20 over 20 molecules are matching, then it is likely we are looking at the same crystal structure. The goal of this work was to apply these comparison methods to structures stored in the CSD in order to identify those borderline cases where the methods differed in their assessment. To do so, we have searched the CSD in 2018 for single component crystals of organic compounds with defined atomic coordinates, without disorder, and most importantly with more than one entry in the CSD. We have identified more than 8,000 ref code families, and we have performed 47,422 comparisons, where we calculated both the powder pattern similarity and the crystal structure similarity. In the majority of cases, the two methods agree in their assessment, and they find the structures to be either redeterminations or polymorphs, with redeterminations having very similar powder patterns, often with similarity close to 1, and 20 out of 20 matching molecules with a low root mean square deviation, whereas polymorphs have varying degrees of dissimilarity in their structures. We have a few cases, well actually they build up about 16% of our dataset, where the two methods disagree, and we have first class where there are 20 out of 20 matching molecules, but the powder patterns are actually different. And a lot of structures that were collected at different temperature and or pressure actually fall in this category. The effect of pressure differences is especially evident, as can be seen in the plot here, whereas the effect of the temperature is less marked. Finally, we have the smaller group where the powder patterns are actually similar, but there are less than 20 matching molecules. If we look at the histogram of the number of matching molecules in these structures, we can see that most of them have actually more than 10 matching molecules in the crystal packings. Indeed, a lot of the structures that belong to this group are actually polymorphs with high similarity. When the comparison is not straightforward, a careful assessment of the differences between the structures is often required. And this can be done by looking at the literature, by using other comparison methods, or even by experimental characterization, such as, for instance, thermal analysis. In general, we have identified 4 principal cases where there is ambiguity, and these can be crystallographic errors, that is, errors that were made during the structure solution, temperature and pressure effects, as I have already briefly described. We can have transitions between high and low temperature phases, and finally we can have polymorphs with high similarity. I'm going to present one example from each one of these classes now. The first example is the pair TEF-GIP and TEF-GIP01 belonging to group 4, where the powder patterns are practically the same, but there are only 2 molecules that overlay. And this is the case of wrong solution for the crystal structure. And in particular, the nitrogen atoms in the aromatic ring in the center were misplaced for TEF-GIP01. This is suggested by the high difference in R values. It's 5% for TEF-GIP and 15.5% for TEF-GIP01. And it was confirmed by the calculation of DFT conformational energies, which and the energy difference for the 2 structures was as high as 51 kilojoule per mole. The second example is this pair, JEDWI and JEDWI06, which are structures of propane, and it is evident that the difference in temperature and the difference in pressure this time are causing the mismatch. So the powder patterns are very different, and 20 out of 20 molecules actually overlay from the crystal structures. And our conclusion is that these are indeed the same form, but with significant compression of the unit cell. And this can be suggested by the high root mean square deviations value for the cell lengths and cell angles. Next one up is EcoBoo, the pair EcoBoo and EcoBoo01, which belongs to group 1, so it will be identified as being the same by our comparison methods. However, it is indeed a case of high and low temperature phases. This is suggested by the high root mean square deviation of the cell length, which is as high as 2 angstrom, and indeed there is, upon a change in temperature, there is a doubling of the unit cell in this case, and the phase transition is confirmed by literature data. Finally, we have a case of polymorphs with high similarity, and this is polymorphs alpha and gamma of aminobenzoic acid, para-aminobenzoic acid. And they have very similar powder patterns, almost 1, but only 18 molecules that overlay. And indeed, if the crystal packings are examined, these 2 structures have matching and mismatching alternating layers of molecules. To conclude, automated structural comparison methods, especially those implemented in the CSD, can be applied to many structures, and in most cases they agree in their assessment. However, an unambiguous characterization requires an in-depth analysis, often paired with experimental techniques, and in the end, the assessment by an expert crystallographer is often required. I would like to thank you all for your attention, and I would like to thank the Giovani Cristallografi Italiani again for organizing this event. Please make sure you check out the other contributions. Thank you and goodbye.